Okay, reaction rates. We've sort of talked about this stuff before when we were dealing about the rate of salvation. But now we're actually going to get into the nuts and bolts of this and how it works. So, what is a reaction rate? A reaction rate is the rate at which a reaction occurs, right? Okay, it is the rate at which a reaction occurs. Yes, I can. Okay, the reaction rate, the rate of reaction, is the increase in concentration of the product versus time. So it's how quickly you make your product. Or, you can go the flip side. It is the decrease in the concentration of the reactants versus time. So you can look at it either way. You can either look at it as it's how fast you're making what you're supposed to make, or it's how quickly you're losing what you are using to make whatever you're making. Okay? Either way, it actually comes out the same. So, for example, combustion processes have very fast reaction rates. Okay, combustion processes are very often things that go boom, and then it's over. Okay, or look at how fast a match lights, and then it's done. Okay, that is a very fast reaction rate. Okay, rusting, however, which is also a combustion process, however, has a very slow reaction rate. Okay, as evidenced by Uncle Wilbur's 52 Studebaker that he has on blocks out in his front yard. It's been rusting a very long time, but it still hasn't completely rusted away. So, no, it takes a long time for that to happen. You guys don't have an Uncle Wilbur with a car rusting on his front lawn? I guess it's just me. Oh, that's right, because all of you guys live in Fresno, huh? That's right, I'm born and raised in Columbus, so. Okay, anyways. Yeah, but my parents actually took me to the dentist. Okay, what are the factors that affect reaction rate? Okay, you guys have heard of these before. These are the same ones that affect salvation. And when we saw the video on Friday, we've already talked about those. Okay, the nature of the reactants, first of all. Just what is reacting? The nature of the reactants themselves have an effect on the reaction rate. Okay. The concentration of the reactants. Nice. Okay, so we've got the specific nature of the reaction, what is reacting, the concentration of the reactants, the temperature and pressure conditions of the reaction, okay, and the particle size and how well mixed is the reactants. Particle size is another word for which feature? Particle size is also is surface area. It's also the surface area. Okay, so if you increase the surface area, you reduce the particle size, or reducing the particle size increases the surface area. All right. So reaction rates are usually measured at the beginning of the reaction, only at the very beginning, and the rate slows down with time as the concentrations go down. Now, what I want you guys to do is to keep this right here. Keep this in your mind for a minute. We're going to go over the next spot, and then I've got a question about this. So, keep this in mind. The reaction rates are usually measured at the beginning of the reaction, and the rate slows down with time as the reactant concentrations go down. All of this stuff, however, is based upon collision theory. Okay, molecules must collide to react. They actually have to physically run into each other in order for them to react. So, only a small number of collisions results in a chemical reaction. So they'll bump into each other, but only if it's just right. Okay, does it actually work? Okay, so the collision must have a minimum threshold energy. Okay, and it must be equal to or exceed what's called the activation energy for the reaction to occur. The collision must also have the right angle of attack, or the correct orientation, in order for the bonds of the product to form. So at this point, I'm going to need a volunteer for a demonstration. Okay, which brings us to our next page. Oh, by the way, I didn't mention the handshake yet. So if you're taking this at home, ask Mr. Allen about the handshake demo. Okay, which brings us to number 3. Without both of these requirements at the same time, no reaction occurs. Particles can actually bump into each other with the correct angle of attack, but if they don't have enough energy, they won't react. Or they could be bullet-to-bullet head-on collisions, huge amounts of energy, and if they don't hit it just the right way, they're also not going to react. They have to have both things. Okay, so here's the question I want you guys to answer. Why does collision theory explain a slowing down reaction rate? And I want you to write that on the side. Your answer to this. Why does collision theory explain a slowing reaction rate? Okay, so as we started decreasing our number of particles that were available to make the right collisions, okay, that means there are fewer collisions, which leads to a smaller percentage of them that are going to be successful. Okay. Potential energy diagrams. Okay, we have a way of actually showing the path of these reactions. Again, on the video on Friday, you guys were introduced to this. Starts with, we start with our reactants, but it shows the flow of energy. Where does the energy go in one of our reactions? Okay, as reaction proceeds from reactants to products, the potential energy diagrams show the flow of energy. Now, all reactions absorb energy as the bonds of the reactants are broken, and they release energy as product bonds are formed. They absorb energy as they break, and they release energy as they're formed. Now, in order for this to happen, to get our bonds to break, we have to get this activation energy, or this threshold energy. And that is the amount of energy required to initiate a reaction. Okay? This is, in the handshake model, this is making sure that your handshake is strong and firm. You have a firm, high-energy handshake. Okay? That is the activation energy. There has to be a certain amount of energy. You know, it's like climbing over a hill. If you're trying to get to the other side of the hill, okay, you've got to climb the hill, and then once you're over the top, okay, it flows easily down to the other side. Okay. At the activation energy, at the moment that these things collide, and they have enough energy, and they made the good handshake with the right angle of attack, with the right amount of energy, and you don't have that icky feeling after you handshake, okay? You have the activated complex. At that moment, it is the transition state between the reactants and the products. And it has the energy at the top of the hill. And you'll see the hill when we start getting into the drawing down at the bottom. Okay, so when they have this energy, the amount of energy, and the handshake itself The moment of contact of right energy, right angle attack, that is the activated complex. Okay. Then we have what's called the enthalpy. And when we get to our diagram, you'll see that the enthalpy is the difference in energy between the reactants and the products. Okay. If you are going to release energy, your enthalpy will be positive, and you'll have an exothermic reaction. If your enthalpy is, if you have, well, I'll show you guys that. It'll make more sense when we look at the diagram. A change in enthalpy then is a change in the heat of reaction at the same pressure. So a positive H indicates net energy is absorbed, and the reaction is endothermic. A negative enthalpy indicates the net energy is released, and the reaction is endothermic. That's what I said, exothermic. Okay, so here are our potential energy diagram. And we're going to label all of these things. So, A right here, A is the energy of the reactants. Yes? That's on the next page, right? Yeah. Okay, then let's put it on there. Yeah. I'm just going to put it right here next to the diagrams, so you can write them on the next page. Yes. And if you cram them all together, it says energy. Isn't that nice? That's clever, huh? It says energy. Energy. Oh, I get it. Okay, B. B then would not be the energy of the reactants, it would be the energy of the products. Then our G of the product. Okay, C. C is the difference between the energy of the products and the energy of the reactant. Now, if you go down from here to there, okay, or B minus A, C equals B minus A, okay, and this equals delta H, which is called the enthalpy so B minus A, it is the products minus the reactants. It's what we finish with minus what we start with. Okay, which, by the way, is the definition of anything delta. Whenever you have delta in front of it, it is always your final minus your initial. It is how something changes. All right, so the change in your heat is called enthalpy. The change in your heat is called enthalpy. And it's going to be the B minus the A to give you what C is. And it'll be in like joules per mole, or kilojoules per mole, or something like that. Now notice over here, if you start higher and go lower, okay, this is going to be a negative number, and you're going to release some energy. If you start low and go high, it's a positive number, And that means energy had to be put into the system in order to make that happen. That make sense? So this would be endothermic. Okay, so that's C. D. Okay, D equals, well, what? What is the amount of energy it takes to get over the top of the hill? This is called the activation energy. I heard it over there. That's the activation energy is D. Okay. And E actually, that's a good question. D is the difference between the energy that you start with and this top point. The place, that top point is indicated, it indicates the activated complex. Okay, it indicates E as the activated complex. It is how all the reactants and products are, for just that moment, combined before it releases the energy and gets to the product. Okay? So the activation energy then, activation energy is always a positive value because this is the amount of energy. You've got to climb over this hill. That's the amount of energy you have to gain in order to make the reaction go. Okay? Delta H is negative for exothermic. Okay, think about what happens here. You start here, you go over the hill, and you end up lower, and so as you go down in energy, that energy gets released into the environment. So that is an exothermic reaction. Okay, and delta H enthalpy is positive for endothermic reactions. Okay. Reaction rate is dependent on the magnitude of the activation energy, okay, or the size of it. The higher the hill you have to climb, okay, the more energy you need, okay, which means the slower your reaction is going to be. Think about this. The more energy it takes for any two particles to collide, to get them to react, the slower your reaction is going to be. Remember, all these particles are flying around, right? Some are faster than others, some are slower. And if the slow ones collide, they're not going to react. So if you raise the amount of activation energy you have, okay, the fewer number of the collisions are going to be there with the right amount of energy in order to make this thing happen. So the higher the hill you have to climb, the harder it is to get over. The fewer molecules that do that, the slower the reaction rate. That make sense? Okay. Fast reactions have a smaller activation energy, while slow reactions have a larger one. So what do you think happens if we raise the temperature? If we raise the temperature, okay, the reaction will speed up because more molecules will exceed the activation energy. The higher the temperature, the higher the average kinetic energy. So if we're increasing the amount of energy of all of the products, of all the reactants, the chances of them having the collision at the right amount of energy in order to react will increase. Not only that, but if they're traveling faster, they're going to collide more often. So it's kind of a double factor. Not only will they collide with more energy when they do collide, but because there's more of them, the chances of them colliding just the right way will also increase. Yeah? That makes sense? Okay, good. That also brings us to catalysts. These are pretty cool. A catalyst, okay, so here's pause for catalyst demonstration. So what catalysts do is they break the ice. they lower the activation energy. They make it easier for the reactants to actually react. In fact, what they really do technically is they align the products, they align the reactants in such a way to make them collide at the angle of attack correctly. You follow that? So they're not just making them go harder, they're also aligning them just right so that they'll react by making their angle of attack correct. Okay. Catalysts also are not consumed in the chemical reaction. If you add a catalyst, that catalyst can go from molecule to molecule and make it happen faster without getting used up. Out. No, temperature in and of itself isn't a catalyst. Temperature increases the probability that the collisions are going to be higher than the activation energy. Okay, and there's more collisions, so the chances of them having the right angle of attack will also increase. All right, catalyst bypasses that. Okay, so here's some examples. Manganese dioxide catalyzes the hydrogen peroxide reaction, makes it go really fast as opposed to just kind of fast. Chlorofluorocarbon, CFCs, this is why you don't see too much hairspray that's psh anymore. It's still out there, but most hairsprays are pumps. Okay, and most psh, psh, rather than psh kind of hairspray, or most aerosols, they've come up with other chemicals, because it used to be CFC stands for chlorofluorocarbons, so that you have this huge carbon chain, and then on either side you have a chlorine attached to it and a fluorine attached to it, and this catalyzed ozone depletion. So it was actually destroying our ozone layer by taking the ozone that's protecting us from ultraviolet radiation, okay, letting us go outside and get safe suntans rather than, cancerous ones, and it was causing a big old hole in the ozone layer in the North and South Poles. The EPA, and there were a number of global treaties and a lot of U.S. legislation eliminated chlorofluorocarbons from the market. You don't use them anymore. We will penalize you if you use them. And over the next 20 years, because this is in the late 70s when it happened, over the next 20 years to like late 1990s, the ozone layer started to return, and it started to grow back so it's like evidence that there is some environmental legislation that actually works and can protect us if we have the resolve to do it. So chlorofluorocarbons were bad. Okay, you guys know this one. What's going to go in this blank right here? Yeah, enzymes. Enzymes are biological catalysts. Okay, we have them. You guys have done the, if you have done the saltine cracker, you guys done that saltine cracker where you chew on a saltine cracker for a really long time? Okay, like for a full minute or whatever, you just keep the same cracker in your mouth and chew and chew and chew and chew and turn sweet. You guys ever tried that? Try it sometime. Okay, I'm not saying it's pleasant. I am saying that you will notice it get sweet. Okay, chewing on a saltine cracker for a full minute is kind of, but it does turn sweet. And amylase is in your saliva. It catalyzes starches into sugars. Okay, and it actually digestion starts in your mouth. And when you eat a carbohydrate, pasta, cracker, bread, it will start to break down into its simpler sugars before it even enters your stomach. Pepsin protease, they catalyze proteins into amino acids. Okay? And lipase catalyzes fats into its fatty acids and cholesterol to make them break apart. Which brings us to our catalyst-activated potential energy diagram. We've only got a couple minutes here, so we've got to knock this out. It is this. The blue on the screen represents the uncatalyzed reaction. Got to go way over for the activation energy to get to there. Okay, this, the green, is when it is catalyzed. You guys see that? It lowers the activation energy, which makes it easier to go from reactants to products because it requires less energy to get over the hill. You see that? This is the result of a catalyst. It just lowers the hill and allows more collisions to happen. Peace.